Hey everybody. Today we're talking about conditional distributions of continuous random variables. We're in a situation where we have a couple continuous random variables, usually we'll call those x and y, with a joint density function, usually we'll call that little f of x comma y. The conditional probability distribution of x given that y, the random variable, has value little y, is just a single variable distribution, and it's essentially just restricting attention to the case where the random variable y has that particular value. The definition of the density function is just essentially your definition of conditional probability. Usually we denote the conditional probability here with the letter g, so g of x given y, and then the definition is that that's equal to the value of the joint density function f of x comma y divided by the value of the marginal density function for the variable that you're conditioning on. So here f sub y of y is the marginal PDF with respect to the variable y evaluated at the value little y. And of course, this definition only makes sense when that denominator is non-zero. Similarly, we can do a conditional distribution for the random variable y, given that the other random variable, x, has a specific value that we specify, little x. The notation there is usually h of y given x, and you can see the definition is exactly the same, just with the roles of x and y reversed. All of these definitions are just variations of the multiplication rule, which I think is always good to keep in mind. So just talking about events rather than random variables, the probability of A and B both occurring is equal to the probability of A given B times the probability of B. The only real difference now is that we're talking about probability densities rather than probability masses, or just probabilities of events. Okay, let's do an example to try and make all of this a little bit more solid, a little bit more real. So suppose we have a probability density function, 1/16 x plus 3y, and the subjoint support is 0, 2 cross 0, 2. So both x and y have to be between 0 and 2. We want to find both conditional density functions and then use them to evaluate the probability that x is less than 1, assuming that y is equal to 1/2, and then the probability that y is less than or equal to 1, given that x is equal to 1/2. So, I recommend trying this on your own, just using the definitions that we already have before seeing how I do these problems. So to compute the conditional PDFs, we're going to need the marginal PDFs, and that means just integrating out with respect to one of the variables at a time. So f sub x of x is obtained by integrating that joint PDF over the support of y. So we're integrating from y equals 0 to y equals 2. We get f sub x of x is x plus 3 over 8. Similarly, for f sub y of y, we get 1 plus 3y over 8. So now we can determine the conditional probability distributions. We can get g of x given y by taking f of x comma y, which we are given at the very start of this problem, divided by f sub y of y, which we just computed. With a little bit of simplification, a little bit of arithmetic, we get that joint probability distribution, that conditional probability distribution of x given y is x plus 3y over 2 plus 6y. Now, while that is a function of two variables, it's best to think of it as a single variable PDF for every single y value in the support. So when we say g of x given y, we are expecting y to be some fixed number. In this case, it's going to be y equals 1/2, and so our conditional probability density function is 2x plus 3 over 10. And you should confirm for yourself that that actually is a valid probability density function on the interval 0, 2. It's always positive, and it integrates to 1 over that interval. Conditional probability density functions are always legitimate probability density functions in their own right. So now we're ready to compute the probability we're asked for. We're going to integrate that conditional probability density function over the area of interest. So here we're interested in x being less than or equal to 1, so we're going to integrate from x equals 0 to x equals 1. When we do that, we get 2/5. We find h of y given x in exactly a similar fashion, so we're going to take a f of x given y, f of x comma y rather, and divide it by the other marginal density function, f sub x of x. Simplifying, we get x plus 3y over 2x plus 6. Here, again, we're viewing this as a single variable function of y, where x is some value that we're plugging in. Then we evaluate the probability that we're asked to find by integrating that conditional density function over the interval of interest. So here, y less than or equal to 1, so we're integrating from y equals 0 to y equals 1. When we do out that arithmetic, we get 2/7. We can also do conditional means and variances, and I would say that the way that we do that is just the most natural way possible. We've got a single variable distribution once we've done our conditioning, so we can find the expected value just by integrating. For instance, in the case of x given y, we're integrating x times g of x given y, either over all the real numbers or just over the support. Similarly, for variance, we are going to use exactly the same single variable formulas. If you try and do these problems just by memorizing those formulas and plugging and chugging, you're going to run into more challenges just because the formulas are ugly and there's a lot of different variables floating around, a lot of different symbols floating around. But it's much easier just to keep in mind that really all you're doing is finding the conditional probability density function, which is essentially a function of one variable, and then computing your mean and variance in the usual way. So for instance, let's go back to this same example that we've been doing and find the expected value of x given that y is 1/2, as well as the variance of x given that y is 1/2. So we already have that joint density function, and we already have the conditional PDF g of x given y. That's x plus 3y over 2 plus 6y. So to get the expected value of x under this condition, we are going to integrate over the support of x here, so from 0 to 2, x g of x given 1/2. When we do out that integral, we get 17/15. So on average, when y is equal to 1/2, x will be about 1.13, 17/15. To get the variance, we're going to find the expected value of x squared, again, conditioned on y being equal to 1/2. So we're integrating from 0 to 2, from x equals 0 to x equals 2, x squared g of x given that y is 1/2. When we do out that math, we get 8/5. Finally, we compute variance by doing the expected value of x squared minus the expected value of x quantity squared, everything conditioned on y equals 1/2. When we do out that arithmetic, we get a variance of 71 over 225. The conditional standard deviation is the square root of that, which ends up being about 0.56. To say that in ordinary human language, when y is equal to 1/2 in this distribution, results differ from that expected value of x by about 0.56, on average, roughly speaking.